specialist at Innovenso Technology. Our company is the leading provider of nanotechnology devices, mainly related to nanofibers production for a broad range of applications. I have my colleague here with me.
Hi guys, my name is Umar. I am the technical support engineer here at Innovenso, and I'll be assisting Bushra here during this webinar.
Today, we are presenting to you nanofibers as advanced filters. Let's look at our program. First, we will present to you a presentation of nanofiber air filters, including explanation of nanofiber usage in air filters and advantages, along with description of the different types of air filters and standards such as EN, ISO, and MERV. Then you will see a demonstration of industrial production process of nanofiber filtration media with our pilot scale unit PE 550 is here. If you have any questions during the webinar, please type them into chat section in YouTube and Instagram. Then I'll bring them up at the end of the webinar where we will have the time for the questions. So right now, let's look at our presentation. Large scale of electrospinning. So first, we have different types of filters. And today, we are going to focus on 3 specific filters, which are electrostatic filters, HEPA filters, and N99 and N95 filtration media. So I would like to give you brief information for each of them. Electrostatic filters, they're using small cotton and fibers. Electrostatic filters create a static that acts as a magnet for dust and other airborne particles. The HEPA, what are HEPA filters? They're highly efficient particulate air filters that are recommended by the United States Department of Health because they're able to remove at least 99.97% of airborne allergens and pollutants. With a MERV ratings nearing 16, HEPA filters provide the highest protection for your home. And then we have N99 and N95. These are media required for face masks with efficiency at least 95%. And then, when we go, can we please go back a bit? Thank you, one more.
One more page.
Thanks a lot.
Yeah.
So here we have applications of air filters. We have mainly 4 applications of air filters, among with others, but we would like to focus on these 4. So first of all, for the face mask, according to the American Academy of Allergy, Asthma, and Immunology, there's a rise in airborne disease, such as asthma, by 12% due to air pollution and other factors. In such scenario, these face masks act as a lifesaver. For the air purifiers, various key players in the market have come up with a new technological air purifier products to tackle human smoke. And lastly, we have air pollution control, APC. So air pollution level in developing countries such as Brazil, China, and India at alarming rate. Most manufacturers of air filter media for air pollution control focus on development on new air filter media to reduce and eliminate the pollutants. And then we have right now COVID-19, and we would like to give you what is the impact of COVID-19 on filtration industry. Mainly high growth rates over the next 5 years are predominantly due to COVID-19, and the demand across this sector is expected to be high. Growth rate of the sector can be reached up to 10% till 2026, according to some market reports. There's also increase in air purification systems in hospitals, with many people suffering from pandemic to provide clean air. Right now, my colleague will, of course, give you more details of why prefer nanofibers in filtration.
Right. So before I go into that, can you go back to the previous slide, please? Thank you. So I'd like to say these masks and these air filters, they have several sorts of standards and tests that clarify them or determine them to have a particular ranking. So what happens is there's an EN rating for Europe, there's an ISO rating for the international scale, and then there's American rating, which is the ASHRAE 52.2. Each of these have their own specific testing. Mostly, they're usually like they align a lot. They're like very similar in many ways, mainly with two parameters, which is the filtration efficiency and the pressure drop. So in certain cases, there are some small differences around, but mainly they're the same. But for the air filters like ISO 29463 and the EN1822, which determine MEPA, MERV, they all have their own specific particular steps that they need to be followed. But yeah, but that's not that's just a small background information about it. What we have here is a slide to show why nanofiber filters are considered more over the conventional glass silica fibers. So they have like four major benefits or advantages. They have high efficiency rates that are comparable and in some cases even more efficient than the conventional melt blown and the conventional pultruded silica fibers. And they have low pressure drop because they incorporate surface loading. They're energy efficient because of that, and overall they have longer filter life. So they essentially the key difference is that they're overall cost effective. So we can move to the next page. So since these have low pressure drop, that means that when it needs to be cleaned with a backward repulsion, what happens is it doesn't have to get stuck in the middle. So what happens is it has overall lower pressure drop, and the particulate matter, they do not get stuck in the middle, and they do not cause any blockage, which is common with normal air filters. These blockages cause the filter to over time stop pores, and overall it stops the quality of the filter, and they need to be quickly discarded. With nanofiber filters, they don't really have such a problem because they don't have this depth filtration issue. So it doesn't have overall has longer filter life. You don't have to use it discard it as quickly. And since the pressure drop is low, the energy requiring to ventilate the air through it is also low. So they're overall energy efficient as well. So let's move on to the next slide. So yeah, high filtration efficiency. So these air filters, they don't need to be, normally when you're talking about air filters that are from silica glass work, they don't really need to be charged because they need to be charged because there's an electrostatic attraction that stops the PM, because generally they're huge microfibers. But nanofibers themselves, they are up sub-micron level in diameter, and because of this, they don't need to be charged. They can stop the particulate matter mechanically. So this is one advantage that air filters have over the of silica glass fibers. So let's move on to the next page. So yeah, there seems to be a problem. The monitor is closed. Right. Okay. Yeah. So yeah, as I said before, pressure loading. So when you're using a filter, over time dust collects onto the air filter, and that dust collects is either on the surface with the nanofibers, or in the case of conventional filters, it's accumulating inside. It seeps into the filter material. So this is what we mean by when it's called loading. Let's move on to the next slide. So the main question is surface versus depth loading. So since nanofiber layers need to be supported by a substrate, they incorporate the particulate matter on the surface. So like I said before earlier, it has surface loaded particulate matter on top of this on the filter. So the dust can be easily cleaned off, and it reduces the chances of clogging. So and higher pressure drop. So let's go on to the next slide. So yeah, this is a picture that shows surface filtration and depth filtration. It just gives a better idea of what it looks like. So you see the particulate matter stopping on the surface and not sealing inside, which is what we want, which is what you see with nanofiber air filters. Whereas in depth filters, depth filtration filters, all the particulate matter gets stuck inside, okay? And that's causing blockage with pores. And when you have these such issues, they need to be quickly discarded. Otherwise, the pressure drop will increase slowly, gradually, and imminently because of the blockage. So let's move on. So yeah, and this is the advantages of nanofiber face masks. So like the conventional melt-blown synthetic material, It can have a filtration efficiency from 95 to 99%, albeit they're much more lightweight. And they, like I mentioned earlier, they rely on mechanical filtration and not electrostatic capture. So that's one other good thing. And because the electrospinning itself is really adaptable, you can add active layers to add additional modifications. And you can use ethanol spray to clean them. Whereas if you were to use ethanol spray to clean melt-blown fabrics, they would easily lose their electrostatic attraction because of the oil. So let's move on to the next slide. So yeah, this is a visual depiction of an animation, so to speak, of our material. So let's run it. So yeah, so our technology incorporates three-ply. So it's basically an active layer in the middle which stops the viruses from going through. The function of the PET non-woven sandwiches, which are in between, which encompass the nanofiber layer, is just to protect it. So the main thing, the functional layer is the nanofiber filter layer, which stops the viruses and allows clean air to pass through. So it's three-layer system. Okay, now we move on to the production of nanofiber filters. So how do you produce large-scale nanofiber media for the purpose of air filters and face masks? So there are two common electrospinning methods, I guess I should say, before we talk about our technology. The needle-based electrospinning setup, which you can see in the picture on the right, and the needleless electrospinning. So each have their advantages and disadvantages. So needles, like the use of needles as spinnerets is what basically determines its of their needle-based electrospinning. It gives fine fiber diameter control, but it's low throughput, so the low production rate does not make it's not easy for you to commercialize it. Whereas in the needleless electrospinning, the spinnerets themselves can be rollers, or you can see in the picture it's a flat wheel. They can be cylinders. This actually this can produce large amounts of nanofibers. The problem being that there will be less control on fiber diameter. And overall, you would need higher voltages in such machines because you're dealing with solutions with higher surface tension. So let's move on to the next slide. So let's talk about our technology. So it gives us the best of both worlds. Our nozzles have this unique design, reservoir design, which allows multi-jet streams. And this gives us the control over having multiple jet streams in a small orifice. So that means lower fiber diameter control and higher production throughput. So this is why we call it the hybrid electrospinning, because it has both the benefits of the needleless and the benefits of the needle. So let's move on to the next slide. So this is just an example image of how it looks like. So this unique design patented of nozzles, they're on a row of rods. So, and we have overall, we're going to show you in the pilot scale, there's like 4 rods, and each of them having numerous number of nozzles. So yeah, which it will emit from. Let's move on. Next page. So yeah, so this is our large-scale production machine. So our machines that are for industrial scale and semi-industrial scale for that matter. They're plug-and-play systems, so they need to be they need really low maintenance. They're just plug-and-play system, which you can do from the control panel. And as you can see in the picture, there's a roll-to-roll system that allows the electrospun fibers to latch onto the substrate media as it moves on, and in the end it just produces large rolls of nanofiber material. So let's move on. So these are my references. I think this is the end of the slides, or the presentation. Let's move on one more time. The next page. Yeah, so we're just going to show you now, we're going to go back to our laboratory, and we're going to show you how to mass produce the filtration media, or how we do it at Innovenso.
So right now, as my colleague Omar mentioned, that we're going to have a demonstration of how production is done with our pilot scale device with PE550. Our device has been installed companies and laboratories around the world, such as Mayo Clinic and Argo National Lab. And right now, before we begin, we would like to show you.
Yeah. So this is an example of an air filter. It's panel shaped. There can be cabin shaped as well, conical shaped. Like there's several shapes. This is just one example of how it looks like. I don't know if you can see, but it's pleated to have better surface area.
You can just get it close. Yeah. Maybe it will be more.
Yeah, it's a bit used, but yeah, this is basically a HEPA filter. Let's just put this to the side.
Yes. So.
So
let's continue our units. So I would like to give you a brief description about our unit, PE 550. PE 550 is our best-selling electrospinning for the continuous production of nanofibers, suitable for manufacturing nanofibers on an industrial scale. Its major advantage is its scalability. So what do I mean with that? It is suitable for both production lines as well as R&D projects. The PE 550 functions with normally 56 nozzles, enabling high productivity for mass production of nanofibers. However, it can also function with single nozzle when working on R&D projects. Its unique design enables the production of nanofibers and composites. It has 4 syringe pumps. As you can see from here, we have 2 in each side. And both, actually, all syringe pumps here, you can use different polymers independently, controlled by the touch panel screen, as you're going to see right here. And we have 4 high voltage power suppliers and down below. And here, if we talk about the touch panel screen, I would like to just briefly mention and show you some. Yes. So here, I think you can see kind of a screen, but there are actually 5 places here where you can control all the parameters separately.
right. So yeah, I guess I can take it from here.
Yeah.
So yeah, this is the control panel right here. It controls, this is where you will be operating the system. You will put in your parameters like the high voltage, the spinning distance, and the flow rate, of course, of the solution.
Yeah.
So what you see on top of here is actually there's a roll-to-roll collector system. You load it from there, and the solution substrates, they move and they roll simultaneously while you are spinning from the hybrid nozzles from here. So before we continue, I already have like solutions set up. Everything is already pre-prepared, but I just wanted to show you that this how we like load the solution. So this is like a 60 milliliter syringe. It's about 30 milliliter right now filled. I'm going to show you how we place it into the syringe pump. So you lift it from here, okay, and you place it in, fine, and you just clip it, you just latch onto it, okay, and this needs to be connected to the polyethylene tubing, which provides it as a channel for the solution to meet all the way to the rods, the metal rod nozzles. So it needs to, like, it basically is providing a channel support, and it's being purged and pushed all the way to the metal rods, where the metal rods are connecting to the high voltage supply. So yeah, so these are 4 overall syringe pumps, and we're incorporating 4 different syringes with solution. This is a PVDF solution. Yeah, so let's set up something here. Okay, so we're going to put in the type of syringe we're putting in. It's already set at the brand model that we already put. Now we're going to place in the amount of solution that we filled. Right now, it's filled with 30 milliliter, so we're going to place 30 milliliter in our machine. Excuse me. So yeah, very simple. It's just you just press it on the HDMI.
You can control high voltage and other.
So the solution, let's start the process. Now what I'm going to do is turn on the syringe pump, which will start purging the solution all the way to the rods that are connected to the high voltage. Right now the high voltage is off, but I just want the solutions to reach to the tip of the nozzle, so that once we activate the nozzles with high voltage, they'll start electrospinning. So yeah, I'm going to turn them all on. The flow rate is now on. So now the syringe pumps are active. You can't see it as much because we're using a very fine meter. So now we're going to put in the high voltage. Okay, now our electrospinning has started. You can see the jets being formed. I'm setting the distance to be 140 at nozzle mode, and I'm going to start the roll-to-roll collector system. So I want the substrate to be moving from left to right, and at the end of the roll, it should be a roll full of nanofiber filter media on PET, on substrate. So let's start. that's rolling, we also want the nanofiber filter media, or rather the nanofiber electrospring jets, to equally distribute onto the polyethylene substrate, trafilate substrate. So I'm going to activate the homogeneity option also in our machine. So now you can see it's moving uniaxially, and when it moves uniaxially, it will basically allow equal spread of the nanofibers. So nanofiber layer to be exact. So yeah, just gonna talk about some certain stuff like while this is happening. Let's see. You have your heat supply here, that basically temperature controller. You have LED lights. You have the safety feature should you need to turn off the machine automatically. And usually this compartment below, yeah, so I'm not sure if you can see it right here. The distance can also be controlled with the linear actuator. Let's make it 100, let's make it 15 centimeters. Right. So you can see multiple jets forming. Let's see from here. It takes a while for it to equal spread, but I think it's here. It's starting now. I guess the next step would be to yeah, so we can move on, but like we can talk about you know, like this filter media can produce, it depends on the, of course, the thickness of the nanofiber layer. You can control the thickness in terms of GSM. So suppose you want N95 filtration media, you can just coat the nanofiber to be about 0.6 GSM for N95. And if you want N99, you can code it to 0.8 GSM. For N99 filtration. So it just depends on the thickness of how much filtration efficiency you want. Let me just. I'm gonna change the feeding mode a little bit higher, so that maybe you can see the jets more readily.
While our system is operating, if you have any questions, please type down in the chat section so we will address them at the end. Because now our machine PE550 is operating, and I believe you're going to have questions regarding to production. We will be happy to answer them all.
Right.
So till our production machine is working, we would like to also answer one of your questions which took our attention, is that what is the filtration efficiency of our membranes?
Right, so good question. We have achieved filtration efficiency of over 98 to 99% for our N99, and in some cases our N95 filtration media. I urge you to contact us further to receive the official documentations and to observe our filtration efficiency of our filter material.
Okay, we are going to come closer to the production so you can see the jets and the nozzle.
Oops.
Also in our machine we have safety door function, correct? It's down here.
Yeah, so we have a safety door function. If need be, once the high voltage is on, you can just turn off the 4-door chambers. But in this case, we're just trying to show you the media. But yeah, if the safety door is on, like if you have the feature clicked onto the control panel, and you open the door, then the machine will automatically shut off. This is one of our safety features. Another safety feature is that in cases of emergency where you need to cut the high voltage supply, we have 3 different buttons to show you. One on the control panel, which is the emergency stop button. The other is the emergency stop button here. If you press that, the machine will close. And then the last one is at the back of the machine. So since the machine itself is like huge, we have 3 different buttons for it.
So maybe we can feed more.
Mm-hmm.
So
I just suggested the flow rate.
Okay.
Yeah, I think it should be good now. So yeah. Right. So is there any other question we have?
if you would like to know more about production and how nanofiber works, please just write it down below so we can address them all. Also, if you would like to know more about our N99 and N95 material, we can also send you brochures and other types of catalog if you reach out to us by email, and we can just talk further and give you more information.
I should also mention that this is the syringe pump system. Normally, in certain situations, you would want to use a peristaltic pump with our machine. So we usually put a tank right here, a tank of solution, as much as it can be, and that incorporates a peristaltic pump, which offers these pulses that pushes the solutions all the way up to the platform. This is something that we can also do with our machine, but right now, for the sake of demonstration, we showed you the syringe pump system. Each has their own different uses and benefits, I would say.
So I guess we have another question, Amar. How will it work on high volatile solvents?
Well, you can use volatile solvents up to a certain ratio. It should work. Well, regarding the previous question, like volatile solution, like up to let's say 35% acetone. So yeah, it should be operational on our machine.
Mm-hmm. As we have previously mentioned, we have 4 different, and adjustable syringe pumps here, and you can use 4 different solutions and control all of them in our touch panel screen. So we have another question. Can the instrument work? Let's see. Just a moment.
Can the instrument work if there were if you were to synthesize zinc oxide nanofibers? Yes, with the polymer, a proper carrier polymer, since zinc oxide itself is ionic, it needs to have a support polymer, a copolymer, so to speak. If you were to mix it well, it should spin into nanofiber form just fine. While we get another question, I also want to take the time to say that certain polymers you need to control the ambience, like the temperature and of course the humidity. So our machines can have a temperature controller, like as I said mentioned here inside the chamber. Also, with an external connection on top, we have our machines can also control the relative humidity. So in certain cases, you need to turn off the chamber, of course, like from here, and control the temperature, which could go up to like say 40 degrees Celsius, and the relative humidity could go from up to like say 20 to 80 to 90 RH.
So another question, able to incorporate small particles or additives in the polymer solvent stream?
Absolutely.
Yeah.
It can.
So another one, what is the basic challenge of your PE550? What is the maximum size that we can produce?
So the reason why it's called the PE550 is because the width is about 550 millimeters, or in other words, 55 centimeters. So that's the constraint when it comes to width, but it can go up to several hundreds of meters, like up to 600 meters in row, while you're synthesizing nanofiber rolls on substrates. So yeah, I mean, you can you can produce various polymers with this. The main challenge for you guys is to optimize the recipe, right? Optimization is key. Just like with lab scale electrospinning, you need to have the certain amount of flow rate and certain amount of distance and certain amount of high voltages, and of course solvents matter to viscosity, stuff like that. If you were to properly after several tests and experimental trials, if you were to properly find the optimized recipe that produces clear cut good nanofiber meshes, you can always use that for the machine. That's the main challenge of the PE550, to work on a polymer and try to find the recipe. Once you have it, then it's smooth sailing from there.
Let's see if we have any more questions.
While we wait, I guess I should mention that the mask we're wearing also is made with this
Yeah, made
nanofiber.
with our material. And
Yeah.
So your another question here is that I wonder how is the cleaning process of the needle? Good question.
So yeah, it's easy to clean the needles, or excuse me, the nozzles rather. You have to basically clean you have to clean it with the solvent that you're using it. If there's in cases of clogging, you just need to use a pin or small needle to open it out. But once you're done cleaning it, you need to for example, if you're using a polymer like PVDF and the solvent is DMF, so to clean it, you would need to use DMF. But for a more generic acid, you can always turn to acetone and water, and then dry it.
It's also easy since our hybrid nozzles designed nozzles that have large holes to prevent clogging.
Right. So the substrate. What was the substrate?
That means
okay. So spun-bonded non. Okay. So we're right now using 35 GSM PET polyethylene trapper plate spun-bond material. Not sure if you can see it, but it's right now moving, and the spin fibers are latching onto it.
Let's address another question. Can water and an organic solvent be used simultaneously in two different?
Okay, syringe pump.
Yeah.
Yeah. So of course you can use 4 different compositions for each pump. So you have 4 different syringe pumps. You can use 4 different compositions for each pump, to create say a blend structure or some mixture. You're of course you're welcome to do that.
Yeah. Since you have 4 syringe pumps, you can use different solvents while operating the system. Let's come close up to the nozzle here. And then you can see here it's spinning and you see the jets moving. What is the temperature and humidity inside the chamber?
Well, let's check because there is a temperature and humidity sensor inside the machine. And from the control panel, right now it says it's about 22.1 degrees Celsius. Let's see if we can focus the camera.
Yeah, we're gonna focus it. Just a moment. Yeah.
Yeah. So it says about 22.1 degrees Celsius temperature and about 48% RH.
Is it possible to check the uniformity of deposit fiber membrane thickness in real time?
Is it possible to check the uniformity of deposit fiber? Okay, yeah. Yes, we can add the calculation and we can check the uniformity. So there's a calculation software to the screen. You can check it from here, and by entering the value of what density or thickness you want, it will accommodate and it will synthesize accordingly.
Yes.
Yeah. All right, so let's move on to the next question.
Maybe we can add, like, to the previous questions that some other parameters it will arrange actually the flow of the fabric by itself according to the desired thickness.
Oh yeah, so like we said earlier, the parameters you can just put them in, and it will arrange accordingly to the flow of the fabric and by itself and desired. Yeah, this all can be accommodated for sure, as I said. So
if you would like to know more technical details of our pilot scale system, please do not hesitate to reach out to us via email, or you can call us anytime you want. So we would be happy to give you more technical details if you would like to, discuss further. What is the quantity of the nanofiber produced per hour?
So I think we measured this before, but it depends on the polymer type you're using. So in our case, when we're using the PVDF, it has a particular like a flow scale, like in meters per hour. So you cannot say the same thing for PVDF or TPU. If I recall correctly, about PVDF could approximately produce 53 meters square per hour on the pilot scale. But yeah, for the N95, I think, yeah, it was the N95 membrane. And like another example is TPU, like 150 grams per hour for the PE 550.
So let's see if we have another questions. Even if you would like to know more basics questions, please do not hesitate to write down in chat section. Another questions, do you give the produced filtration membrane efficiency certification or help your customer to get it?
Sure, we have contacts in local institutions that have these testing hardware that we usually send our membranes to test for, so we can help you with that. So another question is that, is it directly collected on PET or needed to be peeled off? So as you can see here, it's polyethylene terephthalate, the PE substrate. It is being directly spun onto it. It does not need to be peeled off. The point of the PET is to act as a support layer, because generally nanofiber meshes, they tend to be a bit soft and they need substrate material to improve their mechanical characteristics. In which case we chose polyethylene terephthalate because it tends to stick well. Is there any other question?
Another question is that, do you need to stop when the syringe is empty, autofilling?
So for syringes, you would need to, based on the flow rate, but you need to occasionally, like up to each cycle, need to change them when they're running out. So as you can see right now, they're a bit running out. In a while, they'll need to be replaced or refilled rather, to continue production. But in the case of using the peristaltic pump, as I mentioned earlier, there's non-stop production because we are having a large tank of chemicals at the bottom of the machine that's just pushing it all the way up. So it does not require as frequent a change as the syringe pumps.
You see that homogeneity system is working and it's homogeneously coating the fabric. Also, spinning distance can be adjusted by the touch screen for your information.
So yeah, there's a linear actuator installed below, which controls the platform of the spinning distance, as I showed you earlier.
So another question is that, can you use polysulfone with Dichloroethane.
Yes, you have to like it's possible with polysulfone. It's actually an interesting polymer with dichloroethane. It needs to have some modification with the spare parts, like with inert ones, to a specific solvent that is enough to use, or enough resistant enough, resilient enough, so to speak. All right.
So as you can see here inside, we have LED lights
Oh, yeah, I guess we can show
sides.
that.
Yeah, we can just mention in order
Yeah,
you
to see
yeah,
the better,
see and
basically.
understand our
Yeah.
machine.
Also, I should mention these solvents are evaporating as the process is happening. So in large scale production, what winds up happening is you have a lot of solvents in gas form that are that you need to get rid of, especially in large quantities. So our machine is connected to a ventilation system. It has an exhaust fan of about speed of I think 100 CFM, and you activate it from the control panel from here. And what starts happening is it starts sucking up the solvents that evaporate, and it goes directly to the building's ventilation system, just to render the laboratory a bit more cleaner.
So we have another question.
Let's see.
Did you ever spray cellulose, nanocrystals, or nanofibers to make a film?
Yeah, so we added cell nanocrystals to a polymeric solution to give functionalities to a final membrane. So we have done it before, and spraying is also possible. Like electrospraying, it's also possible with our machines.
Our machines are capable of both electrospinning and electrospraying
Yeah.
at the same.
Yeah.
So you can just choose.
So actually, like electrospinning and electrospraying, they're sister processes. They're essentially the same thing. The main difference is that the polymer entanglement density, or how thick the polymer is, or its concentration. So what happens is, just to give you a small scientific background check, as you electrospin and as you put a polymer solution, introduce it to a high electric field, it starts extrapolating in jet form. If the solution density isn't strong enough, what will happen is these polymer threads will start rupturing into particles, snapping into particles, and thus you will get electrospraying. If they're thick enough to not be ruptured, what will happen is you'll get these extremely thin nanofiber lines, and that process will be called electrospinning. It's essentially the same. So we have another question. Let me see if I can read. Which substrates can be used rather than nonwovens? So any substrates can be used. Like that doesn't necessarily have to be nonwoven. It needs to be flexible enough for our machine, though. It needs to be sturdy enough and mechanically strong enough. But it can certainly be used. Of course, you need to see how that substrate also behaves with the electrospun jets. Like it needs to latch on properly, or maybe it'll come off. Those are also some things that needs to matter to be taken into account. Another important thing I should mention is certain substrates, they need to be post-treated, or they need to be a special variant. Like for example, they need to be anti-static, because when you're introducing a high electric field, some compartments, some areas of the of the substrate material media, they get charged, and this causes an unequal distribution. It repels some of the charged solutions. So it's best for you to use anti-static versions. For example, we've used polypropylene in the past, and in some areas it would get ionized. It would get electrostatically charged because of its nature. But now we use anti-static polypropylene to prevent that from happening. It should not hold static electricity, essentially. Okay, so I think we can keep going with another question.
So you're asking, what was the substrate GSM?
As I mentioned earlier, it's a polyethylene terephthalate of 35 GSM. Let me just pause it right here. I think we showed enough here. Just another feature to show you that all the parameters can be stopped from this machine. It can be paused and played again, like so.
Yeah.
So it's really user friendly. It's one of the best things I believe about this machine, is that all the parameters are controlled on a touch screen. in this day and age. What more do you want? So let's see if there's any other question.
For your information, we also use PP anti-static coatages.
Yeah, so like I mentioned earlier about the polypropylene anti-static, it's a little smaller, less dense than the polyethylene terephthalate. It's 30 GSM, whereas we use 35 GSM of PET. Okay, let's see.
So we are just waiting here for your questions, and we will be happy to answer them all. So we have another question. How many cc is max nozzle throughout?
I would say about how many cc is max nozzle throughout? So if you're referring to the number of nozzles right now, we've showed about 108 nozzles. So about 700 milliliters so far of solution per hour. So it depends, of course, on the polymer type. Actually, I should say that. So one example is the example I give you was TPU, about 700 milliliter for 108 nozzles. So it's a case by case scenario depending on the polymer. And when I mean by TPU, I mean thermoplastic polyurethane, which is also an electrospinable polymer.
So for your information, we also offer additional recipe function for all of our machines, where you can save your recipes while you're working, and you can just reuse them after turn off the system. You can just start it and choose the recipe and then go on and continue the production. It's possible.
So let's see. It says different type of layers. Could you move? I can't see the whole question. Okay, can you make a multi-layer material with different types of layers? Yes, by adopting different solutions as per your requirement, you're able to do such a thing for each pump, of course.
With our actually pilot and industrial scale units, it's going to be easy for you to produce a nanofiber layered filters. You can use them while you're producing filters. As my colleague Umar showed you previously, a filter where you can put nanofiber material layer onto, in between the layers or actually on top. It depends on how do you want to use. So it's possible for you to, produce air filtration or any types of filtration material with our unit.
Okay, another question is how many nozzles are there? So yeah, as I mentioned in the last question, for this setup, we're using about 108 nozzles. Yeah, 108 nozzles for this setup. So
for normal PE 550, normally we do have 56 nozzles, but for this unit specifically, we have 108 nozzles for this setup. It could be modified according to the production and, of course, according to the project itself. So let's see.
So yeah, I guess while we wait for other questions to arrive, is there anything else we can mention? Yeah, so as you mentioned earlier, just to recap, it's the pilot scale machine. Okay, it's the second biggest machine we have so far, right behind the NS416 in terms of semi-industrial, of course. The NS416 machine is much larger by default, which has like 1 meter in thickness, width, excuse me, and that's mainly its sole purpose is for industrial large scale production. One of the reasons why I believe this is one of our key machines that are most popular is because it's versatile. It can be used both in this is why it's called semi-industrial or pilot, as a matter of fact, because it can be used in R&D centers, R&D facilities, also in large-scale production. So it's just big enough for large-scale production and also a bit compact in sensitive enough for quality research.
Yeah, as we have previously mentioned, it's possible for you to use only a single nozzle in this unit, and also in some other multi-nozzle units, you can use only a single nozzle and conduct your R&D research along with the industrial production. So we have another question. How we can make negative charge to the collector plate?
Right. So it's like a custom design in our machine. We can like connect that collector to a negative supply output, and we can add it to the setup, and that basically makes a stronger connection and makes the nanofibers traject towards more readily. So yeah,
we can see our actually animation, which we have previously showed it to you, and we can just maybe talk a bit about.
Yeah, I think we rushed over it, so maybe we should follow.
We should maybe focus a bit more of our animation.
Right. So it's a 3-ply system. What I just showed you was the nanofibers being spun onto the PET material. Here, the air is going to the PET. It doesn't have any effect. The air with, of course, the pollutants, and by pollutants I mean particulate matter like viruses, mold, etc. It gets stopped by the active nanofiber filter layer because of various air filtration theories. I believe there's a sieving, there's inertial impaction, there's diffusion, everything and anything but electrostatic attraction, because we didn't these nanofibers are mechanical, as we talk mechanically capturing the viruses, as we said earlier. So it stops them and allows only clean air to pass through. So yes, it's a very simple system. You may wonder that I'm just showing you a PET substrate and we're spinning the middle layer, the nanofiber layer, into it, and then you might ask that where's the other layer? So what our machine can also do, and what we can do with Innovenso, is that sandwiching occurs. We can put another roll of PET, and what happens is and roll it onto the electrospun nanofiber membrane on PET. So what you wind up getting in the end is this 3-layer system of nanofibers. So so we have a question.
Yeah, we have another question. Is the collector stationary? Can it spin?
Yeah, so as I showed you earlier, we activated the homogeneity system. The collector is moving, in fact, forward and backward, uniaxially. So I guess I can show you again.
We can just start the homogeneity.
Just the homogeneity, yeah, I guess it's fine.
So you can just have a look.
So you can see it's having these strokes. So right now, not solution, nothing's on, just the homogeneity. Yeah. It's just moving through and fro, and that way, all the nanofiber jets properly land onto the substrate material. So it is moving.
Maybe we can kind of focus more.
You can also control the rate at which it's stroking and the distance it strokes. How far is it moving to and fro from the center point? Let's make it.
Maybe we can focus on the homogeneity system, and where you can see it's moving like forward and backward, you'll just see very closely. Yes.
So yeah, I just increased the speed for you just to see how it will look. And the strokes, let's reduce the strokes. Let's make them like 20. So as you can see, it's very versatile.
Yes, it's just moving forward and backward as it is seen. Of course, you can control the winding speed left to right.
Now I made it very slow.
So we have another question. What is the substrate used in HEPA producing filter?
Okay, so there are many filters being used. There can be spun bond. There can be silica glass fibers. In certain cases, there are also cellulose filter material too. So it's actually a broad answer. Like there are several types that we can use. But yeah, for our purpose, we showed you the substrate of the polyethylene tryphosphate, which can be used as well for air filters.
We have another question. Can we please come up a bit?
Yeah, can we see the questions?
Yes, please. Thank you. Are the nozzles automatically earthed after the machine is switched off?
Yes, so our machine has a grounding outlet at the back, it's connected. It needs to be externally collected, and once it's connected and the machine is on, within a few seconds, it's a matter of seconds, it gets earthed properly, and you just need to activate the high voltage, and everything is good to go then.
So let's see if we have any more questions. So we have a second question here. Let's see.
How can I get off from evaporated solvents? So yes, as I mentioned earlier, our machine has an exhaust fan. That fan is generally connected with the pleated or whatever of a hose or tube of about 105 millimeter in diameter. It's connected all the way, as you can see, I believe from the camera here, it's connected all the way to your laboratory ventilation shaft or device.
You're gonna see it here.
It evacuates the solvents from there, and it's supposed to be cleaned off that way.
So we have a same question here. Let's answer them again. What is the PET substrate GSM?
Okay, so it is 35 GSM, as we mentioned before, that for this demonstration we use. Yeah, I should mention it's also it's 35 GSM spun bond material. I think we'll solve this.
Yeah, we can just pause the system. Yes, now we turn off the fan.
Fan 2. I wonder if you can hear that. So the fan is on, and now since we're no longer spinning, we can just turn the fan off.
So I guess we are going to have another question coming up. Okay, so we are going to answer it very, very soon. So,
so I guess while we wait, we can also talk about this. We can show the safety feature more in depth. So yeah, so for example, if I need to turn off the machine, let me show you how it works with the emergency stop button. You just press it from here. Let me get it here.
Yes, we can just show you the touch panel.
Or alternatively, you can press it from here. And let's just see what happens when I press it. The high voltage supply is off, the lights are off, everything is off. This is the emergency button. Afterwards, you would want to activate it again, in which case you have to release the emergency button and then press the reset button here at the control panel to make everything start again. And what you're seeing right now is the homogeneity collector reorganizing itself. So it needs to, because, to its center point. So it can be recalibrated, so to speak.
So we have a question here. Which raw materials made active layer nanofiber in mass filtration and in air filtration?
I mean, it really depends. There's several, like nylon 6, PAN, polyacrylonitrile, PEC, polyether sulfone. So there are many types of polymers that you can use for for the functional layer of nanofibers. It's the main reason is they need to be non-cytotoxic, and they need to have a very good, very thin fiber diameter and good porosity and various parameters that stop this. You can also use these nanofibers like PVDF and some other also polymers for not just air filtration. You can use it for water filtration too, because it's, albeit they need to be a little bit more thicker, they need to, the material is still the same, and it's still having the same functions of sieving, and you can use the nanofibers for water filtration purposes as well.
So let's see, we have another question. We're just waiting to see the questions. What is the maximum particle size which can be incorporated in the polymer and solvent stream?
Okay, so wait, what is the maximum particle size which can be incorporated in the polymer solvent stream? Okay, so there is no upper limit so for that. So let's just say so far we've experienced in the tens of microns, so we can't really give you a maximum, a generic cold answer. Tens of microns would be, I guess, your answer. Tens of microns. I'm sorry. I meant hundreds of microns. I should reiterate what I said. I meant hundreds of microns is the range. Let's show you another thing. So we have this on. Okay. Suppose you have the safety door feature on. Okay, and you activate it, right? Now the machine is not going to turn on as long as this thing isn't closed. It needs to be closed for it to function, operate, like operate openly. Because in some cases you would want the chamber to be untampered with, not like no one should like access it. So this machine is not going to work unless if you have the safety door function on from the control panel. It's not going to open. So unless you close this properly, like from here all the way from. But for this purpose, I'm just going to unlock it and reset button should be working. Okay. So again, you can see the collector reorganizing itself, recalibrating itself.
So we have another question. Do you have experience in producing separation material for accumulator battery?
Yeah, actually, it's interesting you mentioned that. That process is not so much different from coating nanofibers themselves. We're experienced with building it, and you can these electrospun nanofibers. They're also used in applications for battery separators, solid-state batteries. So yes, we're experienced in such things called for battery separators. It's one of the key industries apart from filtration and biomedical. When it comes to electrospinning, of course.
Maybe we can also talk about like filtrations in cars, and we have previously sent campaigns to all of our clients and customers that in cars we can also use filtration. Right. So maybe Omar can just give you advantages and how to use nanofibers also in car filters.
Right. So the main difference is they usually have different standards, but the material is basically the same. So for example, combustion engines, they require specific filters for their processes. Now the standard is different. It's ISO 5011 if I'm not mistaken, and but the material remains the same. They just need to meet different criteria to pass as car filters, but they can certainly be used with the nanofiber media. Okay, so we have another question. What is the smallest fiber diameter which can be produced? So in our machine, from our experience, it's about 50 nanometer in scale.
Also for your information, these nanofiber membranes and materials can be used also in HVAC units and systems. As we have previously mentioned, it's also used in hospitals, in-house, and the commercial use or industrial use. It's just definitely used in HVAC systems. And also our material is suitable for using these HVAC units nanofiber layer. It's possible.
One other key function I would want to tell you is that suppose you have a recipe ready, and I understand it gets a little bit complicated and difficult, like when you're mass producing something and you have to keep putting in the same parameters day after day to mass produce stuff. Luckily, in our machine, we produce this data registry, so to speak, which is basically you can save or store your recipe data information in the controls panel. So we have a recipe option for you. You can place in whatever voltage, along with whatever flow rate for that particular solution, and whatever thickness. All of that can be ready-made for you once you've optimized the parameters, of course, and once you're used to the polymer. So once you have a ready recipe, you can just store it as a function in this machine, and you can just click away, and it's one click away from basically starting production and continuing. So we have a question. Did you model this machinery using CAD, and what type of programming was used? Okay, yes, SolidWorks is used to model the device, of course, and AutoCAD was also used for some stuff. Yeah, and also I should also mention that it's the HMI is also a Siemens software.
If you have any more questions, we will be answering them all. Yeah. So let's see if we have any more. Yeah. So in multi-needles electrospinning, the repulsion between the jets would cause localized deposition on the collector, giving rise to uneven thickness. Is this a problem present in your system?
Actually, this is a very good question, a very technical one. So yeah, when you say multi-needles, they have their own electric field, and this causes the jets to have some sort of repulsion. And in different machine systems, you would be faced with some sort of issue. But the benefit of our machine, the hybrid electrospinning, the nozzles, and the homogenization system that we've incorporated in this machine, the machine is successfully able to eliminate these problems of this, this repulsion or interaction between different jet streams and the clogging issues. So we don't have that issue when we incorporate homogenization.
Here, maybe we can just, go over so you can just see more.
So yeah, these four rods have hybrid nozzles, and it's connected to the high voltage supplies for each of them. The channel we're using here is a polyethylene tubing. It needs to be renewed after every use. Yeah, and also the syringes and whatnot. So yeah, and the surface of it. Now you would worry whether if all these various chemicals you're using could damage the platforms or whatever. Rest assured, we've used a very strong chemically resistant and resilient polyethylene polymer for the base, so it should not really damage such certain stuff.
So another question here is that how much is the uniformity of the applied fiber on a flat surface and on a drum?
How much is the Okay, so there are different systems. So in our lab scale, you can have the drum, and for the pilot scale, there's not really a drum. There's a roll-to-roll collection system. So you have a roll loaded here, and as it's being winded up to here, it's being filled in with the nanofiber substrates. So, but the homogeneity is applied. That is applied is basically the same, theoretically.
Yeah. So also we can also mention that we are actually inserting the coating material from this side in our machines. So we are just entangling it from there.
Right.
Another question is here: how are they controlling the humidity of the system?
Okay, so as I mentioned before, our machine, what you can do, we have this dehumidifier connection that is basically connected to the machine. It reduces the humidity of the chamber, as long as the chamber is closed, of course. When it's closed, you can control the relative humidity up to, like, say, from 20 RH to 90 or 100 U. You can control the humidity that way using the dehumidifier. Our machine basically comes with that as a particular upgrade or modification.
There are, of course, additional options and modules which are available if you would like to add into the system. We have a catalog if you would like to learn more about the unit itself, and if you would like to know more about how to produce filtration materials using Innovenso's pilot scale systems, please reach out to us via email. So we will maybe set up a meeting to discuss further on how to produce air filtration or any types of filtration with Innovenso's guidance and setups. So let's see if you have any questions or if you would like to know more. We're here to help you and assist you in every case.
Of course.
Actually, as we have mentioned previously, it is easy to produce, actually, the materials. You can just know how to, proceed with the recipes, the solutions itself. You just need to know the details, and we are here to help you. So another question, where should we come to see the process and discuss details of possible cooperations? So as I have said previously, you can reach out to us via email. We can just give you our emails, sales@innovenso.com. You can just reach out to us and you can just inform us more about your project and production information. Then we can set up a meeting and discuss the possible cooperations which we might have. And definitely we will help you and guide you towards how to produce in an industrial scale or lab scale. Either it's just possible, only you need to just reach out to us. Meanwhile, I can also mention that in our YouTube channel, we have different and several types of videos of our units, from laboratory to industrial. We have those videos, and you can also look at it and watch them all, so you can see the details of our units and production capacity of the electrospinning machines which Innovenso produces.
Well, while we wait for the other questions, I actually thought of something that is actually a very interesting question that's been brought up before too. So you would wonder what material this is made of. So it's a particular type of metals, and you would then ask that why, like if it's a conductor of a high electric field. But in those cases, there's no issue with that because we have a special paint coating for it to prevent it for the charges to move readily. So yeah, I guess this is
So another question, as we have answered previously, how is the cleaning process of the needles?
Okay, so as I said before, the needles need to be cleaned with the solvent they're using in. So, for example, if you're electrospinning a particular polymer with, say, DMF or acetone, it would serve you well to dip or bathe those needles or rods in that solution for a decent amount of time. Then you can just wash it off and dry it with air. For a generic answer, you could just use acetone in some cases, most cases, and just spray onto it. Then use water and then rinse, and of course, and dry it with air. There's some ways. In certain cases, the nozzles right here, you might because of some thick polymers or some difficult to electrospin polymers, they can get clogged. In those situations, you can just get a pin needle and just try to clean the inside. You don't want any blockage inside. You want it to be removed. So once that's out, then you can start properly cleaning it with the solvents.
Since our webinar is more about filtration, I would like to mention that actually our materials are compatible, and it is also matching with ISO, MERV, and EN standards. If you would like to know more details, you can just reach out to us, and we can give you more details.
Right. So I guess I should probably talk about some of the standards about the EN.
Yes.
So we have results for EN 143 and 149, which are basically the European standard for face masks. For the face mask, but I believe the American equivalent would be something of NIOSH. We have Nelson Lab ratings for certain parameters in certain regards. For air filters, there is of course the ASHRAE 52.2, which has their own. It differentiates a bit from the EN 1822 and the EN 779, which I believe now is defunct. But yeah, they're more or less to testing, and we basically are more well acquainted with these results with our air filters.
So another question: are you giving the device buyer filtration media formula? Yes.
So actually, this is an interesting question. So if you need the formula to produce the InnoFilter technology, I believe we can offer that service as a form of tech transfer. But in the case of you have your own specific material and you have a particular polymer that you want to get up and running, and it's very difficult to electrospin, we can provide R&D services for you in which we will experiment these solutions of yours on our machines and spend copious amounts of hours trying to perfect the solution so that it produces nanofiber meshes efficiently.
Along with, of course, our electrospinning units, we offer R&D services such as contract manufacturing, product development, and feasibility studies. If you have R&D project, you do not hesitate to reach out to us. We can just figure it out for you, and we can, of course, give you a right, service according to your needs.
So, what is the working voltage of the instrument, and can this be adjusted? Very good question. I should mention that the voltage we were using for this production of the filter membranes was about 60 kilovolts. But you can, in this machine, you can control it down to like 40 or 20, and as you scale up to larger machines, we can go to a range from like say 20 kilovolts to even like a large amount of 100 kilovolts. It's certainly possible within our range. But generally, pilot scales are up to like 40 kilovolts, and industrial scales go up to 60 kilovolts.
Of course, it depends on the electrospinning unit types. If it's laboratory scale, it's less. However, it's more industrial and pilot, as my colleague mentioned, it's much higher.
Right. Because you have a large amount of solution, and you need to overcome that surface tension, so you need higher voltage as a result for the mass production devices. But for lab scales, when you're just dealing with like say a single needle based system or maybe multi-needle of small Taylor cones, you don't need that much charge or voltage to push it.
So we have another question, I guess. Some large scale device has heat units for a complete fiber dryness and continuous production as a roll production membrane. Have this unit incorporated in our device.
Okay, so in our machines,
we have heat units,
as I mentioned before, we have these these heaters right here, which can affect the temperature. They're at the edges of the platform, as you can see from here. The white peripherals, and another one on the other side. So what happens is you need to close the chamber, this chamber here.
This one.
Yeah. So once it gets closed, once you close it from each end, you can control it from the control panel here, and you can go to atmospheric settings, and from there you can just type in the temperature of what you need. So it'll give you a instantaneous diagram of what the temperature is at the time. So you just press in what value you need, and then you can just press play, and then it will the chamber inside will start heating up to that specific temperature. So this is for those pesky electrospin polymers that need more of kinetic energy and need higher temperature to get up and running. And you can see the humidity real-time action here too. The graphs, I mean.
Yes, we can just adjust it. Yeah.
Right. So right now it's off. We didn't need to show it for our particular media membrane, but in certain cases, in certain polymers, it might matter a lot for you. Right.
Let's see if we have any more questions. By the way, thank you very much for joining our webinar. It's really important for us to see your actually interest in our production. It's really motivating for us to have you here.
All right.
So if there's not any more questions, maybe we can just discuss further about the services that we are giving.
Right.
Let's see if we have any more. Otherwise, we will just focus on different topics. Yes. So we have another question right here. What is optimum fiber size for air filtration membrane?
What is the optimum fiber? Okay, so it's about, for the air filtration membrane, in our experience, it's about 50 to 300 nanometers. I should mention that the nanofibers formed here, you can certainly, to learn more about their nanofiber, their morphology, their porosity, the fiber diameter, the code distribution, all of that, you could certainly run them under test evaluation in a scanning electron microscope, and you can see the fibers like latched on. Like they look like nets, like nano nets on the machine device. So they act as really good. Like it gives a precursor. It gives you an intuitive idea of them looking like these sieves that can stop very small particulate matter.
Thank you very much for your answer, Amar. If you have any more questions, please just send us an email so we can answer them all. I guess today we are done here. We tried our best to give you all the necessary information and, the explanation of our unit and how to produce filtration material using Innovenso's machinery. As I have mentioned, if you have any more questions, please do not hesitate to reach out to us via email. We would be happy to answer them all. So thank you very much for your time and patience, and we will be maybe having you next time in our third webinar. Of course, we will send you an email regarding our upcoming webinar. Thank you very much for joining. So have a great day.